I often think learning mathematics is a bit like a journey. You go from one idea to another as you explore this space of mathematical possibilities over time. Indeed, when you get into some of these ideas to do with, for example, relationships between logic and category theory, this idea that when you're sort of proving things, you're in a sense sort of moving around in some kind of a space or category, maybe a category of theorems with arrows for proofs. This idea of kind of understanding as movement seems to make a lot of sense. So let's try and think about where we've actually gone so far. We started out with the ideas of set theory. And remember, we have this sort of triangle of these kind of three subjects, which in a way are all sort of interchangeable. So there's ways of kind of translating between these three different sorts of perspectives on mathematics. And we started out in set theory, which I've drawn kind of near type theory. And then what we did is we pretty much went to category theory. It's always a good thing to do. And then we've been understanding these ideas of products, co-products, initial objects, terminal objects, exponential objects, and so on. And then we've been going towards logic, okay? So recently we've come across this idea of a Heyting algebra and how that's very useful for understanding things like this partially ordered set of subsets. So remember, this is really the important idea, is that if we have any sets, we can think each of its subsets corresponds with an object. We'll have an arrow from one to the other when the first is contained in the second. And I tried to convince you that that is something called a Heyting algebra, which is just a bi-Cartesian closed partially ordered set. Okay, so that's basically where we are so far. I should say also that this thing's not just a Heyting algebra. It has more properties, and it's actually something called a Boolean algebra. So it has more special properties. But we're really going to focus on Heyting algebras because they have this lovely kind of characterization that they're basically just partially ordered sets which have all the kind of nice categorical gizmos which we've already talked about. And indeed, what we're really going to get to, well, I'll show you, our sort of future trajectory is to kind of come back like this. Okay? So we now want to start thinking about logic and relating it with type theory, and we want to sort of get to a point where we can come up with some kind of a simple type theory which we can then relate back to category theory, in particular this idea of bi-Cartesian closed categories. Okay, so we're going to start by thinking more about what this means. What's it mean to say a Heyting algebra is a bi-Cartesian closed partially ordered set? And the thing is, as I'm sure you're aware, there's a lot of kind of definitions stacked on top of each other in this phrase. But what we're really going to do is we're going to start to express everything symbolically in really quite simple ways. And this is really kind of moving towards type theory in the sense that we're sort of going to start using some very useful notation from type theory to make this look simpler. So I mean, basically, I would say in some sense, we've already encountered like maybe the most challenging things for a newcomer. I think probably the most challenging stuff is trying to get one's head around these ideas of things like products and co-products and exponential objects in category theory. And now really we're just sort of translating those ideas around and seeing how useful they are and using notation to kind of think about them. Okay, so we have structures like these posets of subsets that we're interested in. For one thing, because they're related to logic. And we know that such a thing is a Heyting algebra. In particular, it's a Boolean algebra. And so we want to understand what it means for something to be a Heyting algebra. And we want to start to use some kind of ideas related to type theory. Okay, so I'm going to start to go over the definition of a Heyting algebra again, but this time we're going to use some really useful and good kind of notation, which is going to make everything look simpler. So what are the different things that make a Heyting algebra? Well, firstly, it's a partially ordered set. What's a partially ordered set? It's a special kind of pre-order. So I'd say maybe the first thing about this thing is that it's a pre-order. What is a pre-order? Well, if you remember, it's basically a category. So it has objects like X and Y and Z, and it has arrows maybe between these objects, and we can compose them. But it has the special feature that there's no parallel arrows. We only have at most one arrow going from any object to any object. And of course, being a category, it has these identity arrows. So when we have an arrow from X to Y, we denote that by saying X is less than or equal to Y. Okay, that's just a notation we use. So basically we can say that the pre-order, sort of thinking about it algebraically, we can say that these two conditions are met. So this is interesting notation. What this means, this horizontal line notation, is it's basically saying an if-then statement. So what this is really saying is that if the stuff above the horizontal line is true, then the stuff below the horizontal line is true. So in this case, what we're saying, for example, is if X is less than or equal to Y, in other words, if there's an arrow from X to Y in our pre-order, and if Y is less than or equal to Z, in other words, if there's an arrow from Y to Z in our pre-order, then X is less than or equal to Z. In other words, there's an arrow from X to Z. So this is basically the meaning of this horizontal line. The idea is that if you can show these statements above the line are true, then you have this sort of inference rule which says that if you have this and you have this, then you can get this. Okay, if this is true and this is true, then you can get that this is true. It's pretty much just another way of saying the statement, if X is less than or equal to Y and Y is less than or equal to Z, then X is less than or equal to Z. But it's some very nice notation which we can use to actually make our proofs very, very sort of graphic. So that's one rule. And then this rule here, this is saying that we have identity arrows. Okay, so this is saying that from no assumptions, we have that X is less than or equal to X. So we can always sort of produce this statement. So basically it's always true that X is less than or equal to X, and that's because a pre-order has identity arrows. So this is the sort of notation that we're going to get more and more into as we move towards type theory. But for now, I want to sort of use this notation to talk about these Heyting algebras. And you're going to see that this gives us a really nice notation for thinking about Heyting algebras. And because Heyting algebras are basically sort of just models for intuitionistic propositional calculus, we're basically going to get this really nice kind of symbolic language for talking about proofs as well. Okay, so if you want to think about these things as logical statements, you can think, well, this means that X implies X, and if X implies Y and Y implies Z, then X implies Z. Okay, so let's now do our first sort of proof. Okay, so what's our theorem? Our theorem is that if X is less than or equal to Y, and Y is less than or equal to Z, and Z is less than or equal to W, then X is less than or equal to W. That's the theorem. So these are sort of like the assumptions of the theorem, these three things here. And then we use our rules to obtain the conclusion that we want to get. I mean, if we want to be really precise about things, maybe we can give this inference rule a name. We can call it trans. And we can call this REFL. So that's trans for transitivity. This is the transitivity property. That basically if x goes to y and y goes to z, then x goes to z. And this is what's called the reflexivity property. That, you know, x is always connected to itself. And so we can basically start with our assumptions and use these properties to arrive at our conclusion. Actually, for this proof, we just use transitivity. So we start with x is less than or equal to y, and y is less than or equal to z. Using transitivity, x is less than or equal to z. We're also starting with z is less than or equal to w. Again, using transitivity, we have that x is less than or equal to w. So notice the structure of these kind of proofs. It's basically something like a tree, okay? We have our kind of desired conclusion at the bottom, and then we're kind of using these inference rules. Some of these rules have no inputs. Those would be sort of like nodes at the top of the tree, or maybe the assumptions could also be nodes at the top of the tree. There are some rules we'll find which just have one input. This rule here has two inputs, but all the rules have one output. So we sort of apply them and we get this kind of tree of implication, and we hopefully arrive at our desired conclusion. It's usually a good idea when you're trying to write these kind of proofs to actually work from the bottom up. So you start with what you want to prove, and then you think what kind of rules you can use to kind of translate something into that, and then how could you get to that and sort of build up until you get back to your sort of primitive assumptions or axioms or whatever. So the important thing really, the most important thing so far, is these kind of inference rules, which together let us say what a pre-order is. And notice that this is very sort of computer-friendly language. You could easily make a computer program where you could put some symbols in place of the x's, y's and z's, but your computer can sort of store these kind of pairs with the less than or equal sign between them, and then it could easily sort of have some kind of function which, if it sees something like this and something like this, it outputs something like this, and it can produce things like this. And therefore, if you write down these kind of proofs like this sort of thing, you could easily encode those in a computer. And this is really a kind of step towards these fancy kind of programming languages which are doing things like type theory or dependent type theory. Okay, so the next thing that we'd like to formalize is this idea of a partially ordered set. Okay, so remember that that's just a pre-order with this extra condition that when we have distinct objects, we don't have arrows going between them in both directions. Okay, and we can formalize that by this rule here, which says that if x is less than or equal to y and y is less than or equal to x, then x is actually equal to y. Okay, so we want to carry on describing these different aspects of a Heyting algebra. And remember, in addition to being a partially ordered set, it has to be a bi-Cartesian closed category. So that means lots of different things. One of them is that it has to have terminal object. So we call the terminal object 1, and it's often called the greatest element. And that's because it's really captured by this kind of idea, that it's always true that x is less than or equal to 1 for any x. Okay, so this is the terminal object. It's also called the greatest element. There's lots of sort of words for the same thing in this subject, probably because it's the intersection of so many interesting areas. Another thing that we have is products. Okay, so we call the product of x and y x wedge y, and sometimes this is also called the meat of x and y, and it can also be called the greatest lower bound of x and y. Now these are the rules describing the product, these three rules. So here's the product of x and y, and we have these projections. So x meet y is going to be less than or equal to x and less than or equal to y because of these projections. And therefore, we could think of it as a sort of lower bound of x and y. But it's also the greatest lower bound, because if we have any z, which is less than or equal to x and less than or equal to y, remember the f and g from the categorical definition of a product, these are similar. Well, in such a case, we're going to have that z is less than or equal to x meet y. So this is a lower bound for these things, but it's the greatest lower bound, because if we have another lower bound, then this other lower bound is going to be less than or equal to x meet y. And of course, if our poset was this sort of poset of subsets, then this would be representing the intersection of subset x and subset y. So you can convince yourself that this really does just give us the ordinary notion of a categorical product. It's just that things get much simpler when we're thinking about these sort of pre-orders, because we don't really have to think about arrow composition or these kind of uniqueness conditions, because there's at most one arrow from any object to any other. Okay, so we're going to carry on defining these different features of a Heyting algebra. The next thing we want is an initial object, and we can define that by this rule here. So we call the initial object 0. It's sometimes called the least element, because it's really defined by the feature that is less than or equal to any element x. Okay, and then of course we also have coproducts, and we write the coproduct of x and y like this, x v y. Sometimes this is called x join y, and it's sometimes also called the least upper bound of x and y. Why? Well, it's called an upper bound because we have x is less than or equal to x join y, and y is less than or equal to x join y. That's basically because we have these injections here. So it is indeed an upper bound of x and y, but it's also the lowest such upper bound, because if we have another z, which is also an upper bound, in the sense that x is less than or equal to z and y is less than or equal to z, then we're going to have that x or y is less than or equal to z. Okay? And so this is the sort of lowest one of all of the upper bounds of x and y. And indeed we also know that this this least element here in this kind of context corresponds to the empty subset, and logically it corresponds with false. And this corresponds with the idea of union in this idea of this kind of poset of subsets, and logically it corresponds with the idea of OR. So we're almost done. All we need now is exponential objects. Okay, so the last thing we want for this stuff to be bicartesian closed is exponentials. And exponentials are defined by these two rules here. So we denote our exponential like this, y to the power of x, or sometimes we might write x double arrow y. That's y to the power of x, okay? And if you remember the rules of the exponential, there's a couple of things. One is that we have this sort of evaluation arrow. And if we're thinking in terms of set theory, that would take a function from x to y paired with a value of x and evaluates to give us a value in y. So over here we have this kind of idea. So I mean, we can think of this sort of logically as well. If we think of this exponential as meaning x implies y, then if we have x implies y and we also have x, then we get y. And then we have this other kind of condition which sort of corresponds with the universal property of the exponential object. So it's basically this idea that if we have an arrow from z times x to y, then we get this sort of corresponding arrow from z to y to the power of x. So that would be going like this. And basically you'll see, if you look again at you'll see if you compare this, that this is just the definition of exponential objects and how it kind of simplifies when we're looking at these partially ordered sets. So that's it. We have our full definitions of a Heyting algebra. And there's just so much going on here. We have all these different kinds of operations. And now also we can really understand what intuitionistic logic is all about. You remember earlier when we started talking about logic, we talked about classical logic, where things can be true or false. But here we really have a sort of more general system where we're not saying that things have to be true or false, but we are saying how these kind of logical ideas play with each other. And these are basically our different rules. So when we see less than or equal to, think of that as meaning implies. So now I'm going to read through these laws and I'm going to talk about them in terms of logic. And you'll see that there's a sort of very sensible language of reasoning. And we've already seen how we can actually do reasoning by kind of chaining these inference rules together to make these sorts of proof trees. Okay, so we have x implies x. That makes sense. If x implies y and y implies z, then x implies z. Okay. If x implies y and y implies x, then x and y are the same. Or I could say they're equivalent. Okay. If we want, we can cross off this condition to have a poset, and some people prefer to do that. Okay. We interpret this greatest element, this terminal object here, as true. Okay, so x implies true. So in other words, true is always true. Okay. Also, this product here, we call this and. Okay, so x and y implies x, and it implies y. And then this rule here says that if z implies x and z implies y, then z implies x and y. Seems to make perfect sense, right? And then this least element here, this initial object 0, we can call that false. So false implies x. This is this kind of weird idea in logic that if you have a sort of, if you can get falsity, then you can imply anything from that. It's like if I start doing arithmetic and I assume that 1 equals 0, then I can carry on and prove any equality I like. And it's a sort of strange idea, sort of akin to the notion of a function from an empty set. It's a bit weird. And we've also got this idea of coproducts, and these correspond with or. So x implies x or y implies x or y. If x implies z, y implies z, then x or y implies z. All makes perfect sense, right? And then finally, we have this kind of exponential, which is really a sort of way to encode this idea of implies. If x implies y and x, then y. And also, if we have that z in x implies y, then z implies that x implies y. Okay, so these are our different rules. And basically, intuitionistic logic, I'm speaking kind of roughly, but it's sort of what you can get at by chaining together these rules. And like I say, this stuff's really quite relevant. I mean, why is intuitionistic logic good? One of the reasons it's good is because you're not just assuming that things are true or false. I mean, that's the classical way. You say things are true or false. You can define the meaning of these different words using truth tables, or equivalently using the kind of functions as I described earlier. And then basically you can sort of chain things together and figure out how logic works. The issue with that is that you're always assuming that things are true or false. And that might not make sense in the real world, right? I mean, think about like the Riemann hypothesis. At the time I'm recording this video, that is an unsolved kind of conjecture of mathematics. People don't know if this Riemann hypothesis is true or false. They have not proved it. So is it true or false? If we want to include it, then we couldn't really say either way, right? And there can be things like this in mathematics. The continuum hypothesis which was something which has driven great mathematicians crazy trying to prove, has been shown actually that it sort of can't be proved or disproved within a certain sort of traditional field of mathematics. It's kind of undecidable. And so there can be these kind of results that we can't even say if they're true or false. And so it sort of makes sense to have a sort of logic that reflects that. And really what this logic is all about is really the notion that, well, if I have a proof for this, I can translate it to a proof to that. And it's really this kind of thinking of how can you do things sort of constructively. And this was inspired a lot by the work of the mathematician Brouwer, and I'll maybe be talking more about him later. Okay, so we know, so we can think of this like logic. So let's do some logic then. Let's prove something that's going to come in quite useful. Let's prove that x and y implies y and x. There are some subtle differences between classical logic and intuitionistic logic, but usually if you think of something that makes sense in classical logic, chances are it'll also be a result in intuitionistic logic. It's really quite similar in a lot of its results. So how are we going to prove that x and y implies y and x? Well, there are different approaches. I'll tell you what my approach is usually. I like to translate things into terms of category theory. So what does this mean in terms of category theory? Well, it means that we want an arrow from x times y to y times x. So then I would draw a diagram. Here's x times y and here's y times x. And you see, if we draw the projections and so on, that there is really an arrow. So all we have to do is translate this in terms of the sort of Heyting algebra. And you see basically what we're doing is we're having projections and we're sort of pairing them to get this kind of intermediary arrow, which is what we want. So that's one way of thinking of it. Another way is to sort of work from the bottom up. So we say, okay, this is what we want to prove. And then we look at our different inference rules and we think, what kind of rule could generate this from sensible looking premises? And then we can sort of say, oh, look at this one. It's kind of similar. If we switched around the x and the y and we took the z as this, then we can use this kind of rule. And then if we have z is equal to x and y, we can basically use this kind of rule. So then we can sort of work upwards and we can write these two things down. And then these two things, it turns out that these are just the projections and they're true here and here. So that finishes our proof. From nothing, we have x and y implies y and x and y implies x. And then together those two imply x and y implies y and x. And we're done. And the idea really is that now we've proved this, we can almost just think of it like another rule that we can just use straight away. So it's almost like kind of writing procedures when you're computer programming. Once you've got a program that can change the input to an output in a certain way, you can just kind of record that as a procedure and refer back to it later. Okay, so the next thing that we want to prove is that x and true is the same thing as x. So we can really prove this. I think a good way is to write the results and then think about what rules we can use. So firstly, we have an equals here. And there's only one of these rules that generates some equals, and that's this one. So we use anti-symmetry. So if we have that x and true implies x, and x implies x and true, then that'll do the job. But is this so? Well, we can see that this is actually the case because it's basically just a projection. Okay, it's just this rule. How about this one? Well, we have something implies something and something. So we want this rule. So if we can get x implies x, which we have here, and if we can get x implies true, which we have here, then we're done. So that finishes this proof. Okay, so here's our next theorem that we want to prove. We want to prove that if A implies A dash and B implies B dash, then A and B implies A dash and B dash. So let's go. Again, we start with our desired conclusion, and then we think, well, how can we get this? And then we look over here and we go, okay, maybe we can use something like this. So we can split this into these two. And so now we just want to prove that A and B implies A dash, and that A and B implies B dash. And so let's just have a look at how to prove this one. Well, what we can do, we can use transitivity, okay, because we know that we can get that A and B implies A. That's just this sort of first projection here. And we're also assuming that A is implying A dash. And we can just do something similar up here, okay? So if we can get A and B implies B, and also B implies B dash, then again we can use transitivity to prove this. And this is essentially an assumption, and this here is, I suppose you could call it an axiom. It's this second projection here. So that's the proof of that. I think it's such a pleasant thing to be able to do this because, well, there's so many reasons. You're understanding intuitionistic logic. I mean, a lot of people, you know, logic is all around us in the world, and I really find it remarkable, like how kind of peculiar this kind of intuitionistic logic is, because of course understanding logic is absolutely critical for all sorts of decisions that we make in everyday life as well as in science. But you know, the fact that we really need to think quite hard and have some quite elegant theories in order to be able to deal with things like intuitionistic logic seems to me to be a good reason to study it. Also, topos theory. If you have a look at topos theory, it's a very beautiful theory, and the way the sort of topos logic is basically this sort of logic. Indeed, if you look at a lot of sort of modern mathematics, it's built on this kind of intuitionistic logic, homotopy type theory as well. So it's so worthwhile to study it. And also, as you do all this, you're really doing category theory, right? I mean, we could basically pitch this as the kind of timesing together of two arrows. It's all the same in some sense. And so it's very pleasing that you can sort of combine so many different disciplines and ways of thinking in some really quite simple sort of notation. So I would really encourage you to, you know, think of as many kind of statements which are true in logic as you can and try and prove them in this sort of framework. Okay, so the next thing we want to show is something that's really useful, and that's basically that this sort of transformation can actually go two ways. So we can go from this to this, but we can also go the other way around. Okay, so if z implies the exponential, then z in x implies y. Okay, so here's a proof of this. So we want to start with our conclusion, z in x implies y. And how are we going to prove it? Well, the way I like to think of it is that we're assuming we have this arrow here, okay? We're having this as a sort of assumption that z is less than or equal to y to the power of x. And so we can use that to make this kind of times together arrow, and then we can compose with this evaluation arrow to get what we want. All right, so we're going to be using composition here, so that corresponds with this transitivity rule. So the kind of step before what we want to get can be z in x implies y to the power of x in x, that's this arrow here, and also y to the power of x and x implies y, that's this evaluation arrow here, which we have as a sort of axiom. And so we just need this. And we can use this kind of timesing together arrows kind of idea to prove this. So if we can just prove that z implies y to the power of x and x implies x, which we know is true, then we're done. And indeed we have this as an axiom. So using this, we can use these two to prove this, and then we can finish our proof. And this is really great because it means that this is a kind of two-way street. And sometimes I like to denote that with sort of double lines here, to show that we can translate not only from the top to the bottom, but also from the bottom to the top. So this implies this, or this implies this. Or if you like, this holds if and only if this holds. Okay, so now we finally get to really quite a sort of lovely understanding of what these exponentials really mean. Because we've basically shown that this law here works two ways. Okay, we took it as a sort of assumption in our theory that this implies this, but then we also proved that this implies this. So we can go two ways. So if we take this expression and then we replace the z with a true, we get something really, really remarkable. So we get this kind of expression here, that true and x implies y is equivalent to saying that true implies this exponential thing, which I also like to pronounce as x implies y. And the reason why I like to think of that as x implies y is going to become very clear momentarily. So firstly, recall that we have this equality. We've already proved this, that x and true equals x. Or we've also shown that this is the same thing as true and x, because I've already shown that a and b is the same thing as b and a. All right, so then it follows that we can translate backwards and forwards between this line and this expression here, x less than or equal to y, or x implies y. But look what else is going on. We have that true implies y to the power of x. And also, using this, we automatically have that y to the power of x implies true. And using anti-symmetry, we then have that basically this is equivalent to saying that true is equal to y to the power of x. And so the critical thing here is that this top line and bottom line are equivalent. So in other words, saying that x implies y is the same thing as saying that y to the power of x is true. It's exactly the same, has exactly the same meaning in our theory, really. And therefore, we might as well pronounce this as x implies y. And therefore, because this is really an exponential object, so we can think of sort of, and since this is really a sort of exponential object, it's really encoding the kind of arrows from x to y. And therefore we can sort of identify the arrows in our theory with this idea of implies. And it's all formalized with this notion of the exponential objects. Okay, so now we understand Heyting algebra, and it's a beautiful thing because a Boolean algebra is a special kind of Heyting algebra, just like classical logic is a special kind of intuitionistic logic. And therefore, when we're playing around with Heyting algebras, we're gaining understanding of logic, but also we're really gaining understanding of bicartesian closed categories. And they are in so many places in mathematics. Okay, so it's really worth understanding. And really the central idea is this kind of notation. A is less than or equal to B. And we've been thinking about logic, we've been thinking that might be interpreted as A implies B. Or if we want to think in terms of category theory, that means there's an arrow from A to B in our partially ordered set. Now, there's another bit of notation, and I'm sort of moving towards type theory now. So it's another piece of notation that's sometimes used in logic, which is A entails B. And roughly speaking, it kind of means something similar to this. Okay, it means that if we have A as a hypothesis, then B is true. All right. So I mean, really, you'll see this kind of notation, like under the hypotheses, the A1 and the A2, and all the way up to AN. Under these hypotheses, we have that B is true. And really, for us, because we have this language of hating algebra now, we can think of this as really meaning the same thing as A1 and A2 all the way up to AN implies B. Okay, so that's a little bit about this. However, if you want to do logic and you want to think about proofs and things like that, you're not always just wanting to say, well, that's true, and that's true, and that's true. You probably want to be presenting evidence. You want to actually be constructing proofs. And we can do this. Okay, so now we get to this notation. So I'll speak roughly about this to begin with. If this means that A entails B, it kind of means that this proposition B follows from this proposition A. What this means here basically is that when we have evidence little a for this proposition capital A, then we have this evidence little b for this proposition capital B. So this is similar to what we've been talking about before, except we're sort of thinking about proofs now. So we're sort of thinking, if I have this proof little a for this proposition, then I can get this proof little b for this proposition. Now I'm going to be a bit hand-wavy here, but what this basically says is that a proof of proposition A can be translated to a proof of proposition B. All right, and it's nice because we can think about that kind of situation in terms of our partially ordered set. Think about this scenario where there's an arrow from capital A to capital B. Now, if there's an incoming arrow into capital A that we might call little a, then we can translate that to become an arrow little b, all right? And this is this kind of intuition about how everything's connected together. This idea of having one proposition implying another one is basically telling us that there's a way to sort of translate evidence for this proposition to evidence for this kind of proposition. So, for example, if we put a 1 here, it would be saying that if A is true, then B is true, okay? Because we can translate this kind of evidence for A, because we can translate this sort of demonstration that A is true here to this demonstration that B is true using this arrow. So now we can start to talk about type theory, where this kind of thing is usually thought of in a very different way, but we're going to be seeing that it's just another side of the same coin. Okay, so I'll write it in yellow. What does this mean in type theory? Well, it sort of depends in a way. I find the kind of phrase type theory a bit misleading. Maybe it should be called type theories, okay? Because really there's lots of type theories. There's lots of these sorts of games that people play shifting around symbols according to different rules, but which make theories which describe different things, and they're called type theories, okay? But usually, especially in practical situations when people are programming and things, when they write that kind of thing, they're really meaning, they're sort of modelling some kind of data structure, capital A, and they're saying that little a is a value in that data structure. Okay, so one of the first kind of applications of type theory was trying to model what's going on in set theory. Okay, so one thing you can think of this as meaning is simply that we have this set capital A, and it means that little a is an element in that set. That might be what it means. It depends on what kind of type theory you're talking about. But there are type theories which are basically designed to emulate what happens in set theory. So as a first at first glance, you can think of that as meaning that little a is an element of capital A. Okay, so fine. In that context, what does this mean? Well, it means that if you have an element little a of capital A, then you have an element little b of capital B. And the important thing about that is that this is sort of the context. Okay, so let me give you another example. Suppose, just talking about elementary arithmetic, okay, suppose I write x plus 1, and I mean plus as in adding 1. So what does that mean? Well, we don't really know what the x means, okay? If we're being really literal about things, like a computer might be, it might say, well, I just don't know what x is supposed to mean. So we really need a context for this kind of expression. We need some kind of background information, which usually is kind of lying somewhere in the back of the mathematician's mind as they're working. And one of the things we like to do when we're thinking about things like type theory is to make everything explicit. So we could say that this is a number, okay, so this thing has the type number. I'll write n to denote the type of numbers. So for now you can think of this as meaning the set of natural numbers, if you like. So we're saying that x plus 1 is an element in the set of natural numbers, although, you know, that's not exactly what I mean, but it'll do for a working understanding for now. So we could say that in the context where x is a natural number, we have that x plus 1 is a natural number. So here we're using this symbol here, which is sometimes called entails. We're using this symbol to mean that in this context, or with this hypothesis, we have this, okay? And notice that this expression now is allowed to depend on this value, okay? Because we've kind of defined it within our context. And so when I write this kind of thing, we'd say that this here is a variable of type A, okay? Because this isn't really, because the way we normally think of this in type theory, this isn't really something which we have specified. This is just a sort of general value of type A. But given this, or in this context, we have this, which we'd say is a term of type B. And just like this is a term of type n, and this actually depends on x, it might be that this B here depends on A. So critically then, it could be that this B here is actually some expression that depends on A. All right, it might be, we might have some arrow or function f from A to B, and then it could be that this B here is equal to f of A. So if you now think again about this, I wish this was taught more at school, because I think kids, when they're learning mathematics, I think they have a hard time actually understanding the idea of variables. And I kind of know why, because it's like so hard to explain. What do you mean by x when you write x plus 1? But what I would say that this means is it's really defining a function, right? It's defining a function from n to n, which takes in an input and then adds 1 to it. Okay, when we say it like that, we don't have any more of this kind of hard to talk about notions of variables. And in a similar way, when we have something like this, we can really think of it as a sort of function which goes from capital A to capital B. And it gives us this value little b of type capital B, which might depend on A, or it might not. It might be a constant valued function. That would be fine too. Now, when I say function, I'm sort of slipping into this habit of thinking that our type theory is expressing what's happening in set theory, and it may not be, okay, but I'm trying to talk roughly to give some sort of intuition. And then this kind of idea can be extended to this sort of notion. So again, let's kind of shift back to thinking about logic. When we say if we have evidence of A, then we can get evidence of B. Now, if we're thinking about the Heyting algebra, then if we say that statement A implies statement B, then there's really just kind of one arrow from A to B, one kind of way to translate this evidence of A to evidence of B. However, there might be more general situations, like we know that there can be like many proofs of a particular theorem. And it's interesting actually to look at those proofs and then investigate what the similarities are. I mean, that's one of the wonderful things about this subject. Like, mathematics is like heavily focused on proving things, but this kind of thinking allows us to sort of do meta-mathematics and really think about what it means to have proofs, what the structure of things going on is. And so, rather than just thinking about a bicartesian closed poset, where there's sort of just one arrow from one object to another, at most one arrow, we can think of a sort of general bicartesian closed category. And this is going to be our setting for our first sort of type theory that we're really going to lay out the rules for. And so in that context, when we write this kind of thing, we're sort of saying, if I have evidence for A, I can get evidence for B. And that's sort of saying that I have an arrow F from object A to object B, if we're thinking of these things as objects in our bicartesian closed category. But there might be many arrows from A to B, many ways to translate evidence for A to evidence of B. And maybe there are sort of non-equivalent ways to prove that A implies B. And also we can write this kind of thing, okay? So if you think about this in terms of logic, what it would mean is that if we have this evidence A1 for capital A1 and evidence A2 for capital A2, all the way up to this evidence AN for capital AN, then we can get this evidence B for this proposition capital B. But if we think about this in terms of type theory, what it would mean is that if we have these values here of different types, like this value A2 of type capital A2, well then using this, or in this kind of context, or with these sort of variables, we can get this term little b of type capital B, which is basically kind of just defining an arrow from this product, and notice I'm using times now instead of this kind of meet symbol, because we're potentially dealing with a richer sort of category that might not just be a partially ordered set. And so we can say that there's an arrow from this product of A1 times A2 all the way up to AN to B. And in terms of sort of everyday set theory, that just means we have this function with these which takes these n inputs and gives us this output, which is of type capital B. And then again, thinking in terms of proofs, that's kind of like a way that if you have evidence for all these required things, you can generate the evidence for B. So now we're really starting to understand this connection between logic and type theory, and also with category theory, everything's coming together. And so the next thing I want to do is to describe this kind of simple type theory, which is basically going to be the type theory of a bicartesian closed category, a general one. Or we could say it is basically lambda calculus with sums, if you like. And so I want to emphasize that everything I've just said about type theory is just rough, okay? I just wanted to give an outline of what's going on. When I get into the next video, I'll be speaking about a particular type theory more precisely, and that's actually a lot easier.